Okay, let me get started. So I don't have the slides, so this is going to be a whiteboard session. Okay, let's get started. First, what I'm going to talk about today, right? So today I'm actually going to talk about, I call it math behind proof aggregation. So first, let's motivate what is proof aggregation and why we need that and how can we use that. Like we all here to try to learn more about ZK, and ZK is useful because it could extend the computation in a privacy preserving manner without losing trust. So essentially, the way I view it is that the most important public infrastructure is like consensus, right? Consensus is a shared, like a codified value. So like this is like a public infrastructure all the people can share. However, there's the inherent difficulty of consensus is that every node have to repeat the same computation, so the computation becoming very expensive. And ZK is basically a way you can extend the computation like nearly kind of for free, because now instead of doing the computation, you can verify the proof, right? But the problem here today is that, I mean, we don't have a lot of like ZK applications right now today on public blockchains, for example, on Ethereum. There are various reasons for that. There are some technical difficulties because even today it's still very hard to build a zero-knowledge proof-based applications. There's also other difficulties. One of the difficulty is that it's actually very expensive to verify a proof on chain today, right? Any audience have ever like build a ZK application or write a ZK circuit and make it like verify it on Ethereum? Please raise your hand. I guess let me ask one question. What's the gas fees? Let me choose a different color actually. For verify gross gain or Planck proof. Ethereum. Anyone know?
I'm guessing somewhere around 100,000.
Okay, answer one. 100K.
Yeah.
Any other answer? This is not too bad answer, but it's still underestimate. Oh, 1 million or 200, 1 million. Yeah. So I mean, there are good answers roughly on the same ballpark. The actual answer I will write here is basically 200K plus, because 200 is the basics. You need to do a bunch of like MSM, like a multi-scalar multiplication and pairing. So why it's plus? And because this is dependent on the like the size of the public input, right? I'm not sure previously, have you guys covered what is a public input? I will just briefly mention it, but will not like dive into it, right? That's for gross 16. And for Planck, it's more about like a 250K plus. And it actually depends on more factors. First is number of columns in the Planck configurations, and also public input. So that's a Planck. So there are different implementation Planck, for example, Aztecs Planck or like a Halo 2, right? You can see it's fairly expensive to verify proof function. And one idea here is that in order to get down the cost, one idea here is that we can do proof aggregation. Proof aggregation means that suppose we have multiple different proofs, let's say pi 1, pi 2, pi 3, and pi n. And now, instead of verify this single proof on chain, we build an aggregate proof, right? So let's say we call it pi AGG. And this aggregate proof, so the statement is a conjunction of all these proofs, which means it's a recursive proof to prove that the verification of pi 1 to pi n is true. So we can write this like pi 1 and pi 2 and pi n, right? So far, so good. The difficulty here, sorry, any question? So the difficulty here is how we exactly to do that, right? There are like various ways. So the most fundamental idea here is that we're using recursive proof. So the most naive idea is that why not we just build a circuit, and the statement of the circuit is a verifier to verify. So we build a verifier circuit. Yeah. And now, do you want to ask a question? So please mute, yeah, if you don't ask questions. So let's say we build a verifier circuit. The most naive ideas is that we build this like a verifier circuit, and then we combine like a, let's say a single batch, we have 8 proof. Then we kind of stacking like an 8 verifier circuit together, right? In a single circuit, we have verifier, and verifier. There is nothing wrong about it. The problem here is that it's not very efficient. So we can using the improvement ideas is that we can use some more clever tricks to so basically, I guess let's take a step back, right? So this is basically our like an aggregation circuit, right? There is nothing wrong of just like stacking multiple verifiers into the aggregation circuit. The problem here is that this circuit is going to be very big. And I will dive into some of the sort of the mathematical reasons why this circuit is very, very big. But you can right now just take what I said as granted. So the way to improve that, then we kind of need to getting into a little bit details about how a proof verification will be doing. For this today, we kind of limited to only like a Gross 16 and Planck proof. So for both Gross 16 and Planck proof, from a very, very high level, we can break the proof verification process into 2 steps. So the first step, we call it phi prepare. I wouldn't dive into the details of this. What is a phi prepare? Mostly it's a bunch of MSMs and some scalar multiplications. MSM is like a multi-scalar multiplications. And some scalar multiplication here, I mean the like a finite field multiplications. All right. And then last step, there is a pairing. So again, I wouldn't, right now, I wouldn't dive into the pairing, but just from the grand scheme, right? You can see, if we are aggregating 8 proofs, within the verifier circuit, we need to implement this like a phi prepare and this like a phi pairing. And both, they're very expensive. So the idea here is to improve the proof aggregation performance is that we implementing a new verifier circuit. This verifier circuit only implement phi prepare. So we have eight of them. And for phi pairing, what we do here is that suppose we have 8 pairings, right? We basically take a random linear combination of the pairings. So we just combine the 8 pairing to a single pairing. So this is a mathematical property we can use for pairing so that we can leverage here. So you can see we actually move a big chunk of very expensive computations out of the circuit to make the aggregate prover more efficient. And so this is essentially how does, for example, Halo 2 proof aggregation, or like there is a proof aggregation technique for Gross 16 snark pack work. We'll dive into more mathematical details here, but this is like a high level framework. So I will pause here for I guess 30 seconds to see any questions so far. Okay, great. Let's move on. So by the way, this like a random linear combination, this is still a circuit, right? It just like we only need to implementing like a 1 pairing instead of 8 pairings in the circuit. Okay, great. So one of the key technical difficulties and one of the key technical challenges for implementing efficient proof aggregation or recursive proof is a thing called I think you probably find some of the like more technical ZK people they are talking about is called like non-native arithmetics. It's a quite kind of a lousy word. It's kind of a word salad. What exactly does it mean? So let's dive into that. before we're actually dive into that, maybe it's good to give a little bit refresher on on some of the basics of the ZKP. So first, what is ZKP? I think ZKP is a proof for a relation, and let's say R. So this R is in MP, right? MP is a computational complexity class. What do people usually write here? So people usually write, we can define a relation, and basically, like we write XW in R, right? We prove that how can we precisely state, like what's the meaning of the proof? The proof means that we know the witness with respect to the relation and with respect to some public input that is public to both verifier and prover. And we're normally using X to indicate the public input, and we're using W to indicate witness. Let's do an example here, right? So I know a statement could be, I know a pre-image of a catch-check value hash, which value is like a 0x, 5, 6, whatever, right? So what is the relation here? Anyone? So here I stated the zero-knowledge proof. The zero-knowledge proof state I know a pre-image of the catch-check hash, which the value or the digest of the catch-check hash is this particular value, let's say 0x, 5, 6, blah, 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 right? So I think it's good to have this like mental model of a ZKP using this kind of like a formalities of public input, witness, and relation. So my question here is, what is the relation in this particular zero-knowledge proof?
The pre-image and the hash value. Right.
Why?
Since we can hash a pre-image and get the hash value, so I think they form a hard relation, right?
Right. I guess what is the public input?
The hash value and the catch-check function.
So public input means some value both known to the verifier and prover. So here, the public input can only to be the hash value, because we're proving that we're actually proving that like I know the witness of this like pre-image. I know the pre-image of this hash digest. I think someone actually answered correctly in the chat, right? The relation is a hash function itself. It's a computational function. What is a computational function? Computational function means given an input, you get output. The computation function, so how do you think about relation? You can think about relation as a two-column table. Right, here is the input, here is the output. If you can enumerate all the input, and this is like could be an infinite amount of tables, then that's a relation, right? Then the relation is a hash function itself, as someone like correctly answered in the chat. So the hash function is a relation. The public input is the catch-check digest, and the witness is a pre-image. the zero knowledge proof said, I know the pre-image, but this is private. I don't, in the kind of academic terminology, the prover doesn't reveal to the verifier what exactly is the pre-image the verifier knows. Okay, so that's the that's essentially about ZKP. Okay. So also the second thing I want to say here, it's a lot not related to ZKP. It's more about the implementation of ZKP. Is like a finite field. EC here means elliptic curves and pairing. So here I just want to ask, have you guys go through some of the basics before? If you have go through this basic before, I will just do a quick capture. And if you haven't, I can do slightly more detail. So I guess, okay, cool. Someone knows the basic. Okay, so first for the person who knows the basic, can you tell us what is a pairing or bilinear map? Okay, let me just go through it. Just like let me know if I just like getting to yeah, computation between that's roughly about right. Yeah, let's try to go through it. We'll see. So first let's talk about the finite field. What is a finite field? So like roughly speaking, a finite field, you can just think of uint like a mod p, and a p is a prime number. So there are some like deep mathematical reasons why people want to define finite field in that way. So the reason here is like a group theory. It's the reason here is a group theory effect. So this group theory effect says any cyclic group with order n will be isomorphic to this group Z mod. Sorry, Z. This is like the coset defined by Z divided by NZ. This is like a quotient group. Okay. For simplicity, we don't have to care about this like fundamental math reason I just mentioned here if you are interested. So then let's talk about elliptic curve, right? Elliptic curves could be defined by set of equations such that y squared equals to x cubed plus 4. All right. This so and then let's dive into that, right? So first here in the cryptographic settings, the elliptic curve we defined is defined like on a defined in field. So here, what it means is that in the elliptic curve, right? Let's say we have a point, and this point is the coordinate is x0, y0, and here both x0 and y0 belongs to this finite field. So this is like a finite field operation, right? You might say, like, why bother? Like, why we need like elliptic curve, right? We have finite field, seems good enough. So the fundamental reason here is that crypto is based on mathematical assumptions, or means that the cryptographic security need to be reduced to some like a mathematical hard problems. And a normal use of the mathematical hard problem we call the D-log, which means like we want to using the fact that the discrete log of some mathematical object. I will be a little bit blurry here. I will tell you exactly what the mathematical object here. The discrete log of this mathematical object is hard. So, and the mathematical object here, we're talking about group. Why? So I guess to see how we're getting here, like any audience want to volunteer, what's the difference between a field and a group? Okay, Peter said close under multiplication. Can you articulate? Yeah, you can open the mic if you want. Okay, not really sure. No worry. So the difference of the field and group, please like look up to the Wikipedia. This is quite important, right? So they are both kind of like a abstract, like a mathematical object to define a bunch of things. In group, you only have one operation, and people can use different notations, like a multiplication or like addition, doesn't really matter. The group, you can only define the single operation. So group only allows you to do the single operation. So let's say if this operation is defined, yeah, iPhone said every field is group. That's true. That's true. But that's like, we shouldn't view it that way, right? Because the group is only have like the group. So when we're talking about group, right, where the group is not the element, the group is an element and also the mathematical operation, right? So, so like that I think that's a fundamental way of thinking about this. But nevertheless, right? So a group is. Let me actually try to. Seems that not so many. Seems that not so many people actually getting into this sort of the group theory primer. Let me actually write here. I think it's still quite important. Okay, what is group? So a group is a non-empty set with an operation. And this operation, we can write it in the multiplication, that's fine. And sometimes you can use in addition. There are some like underlying, there are some like a sort of underlying convention, people are using notation, but that's just using the multiplicative notation here, right? Okay. Then we want to having several things, right? First, this operation itself is closed. Closed means that for any A and B, let's call this group G, right? In this group, A times G, B is still in the group. So that precisely means closed, right? Secondly, is that there is an identity element. So normally people just write this identity element as 1. So by the way, this 1 is not insured. This 1 is just like a special group element. So basically, the identity element means 1 times A equal to A, and A times 1 equal to A. Okay. Third, this group operation is associative, which means A times B times C equals to A times B times C, right? Last but not least is that there is an inverse for every group element, which means for all A in G, there exists B such that B times A equals to 1. That's a group, right? You can see it's very simple. You only have this like then you only have this like multiplication. Okay. So then how do you define discrete log? Discrete log is just like A times A times A. If we have Ka, we can write this in the explanation form. Discrete log is hard, precisely set in this group, right? If you know the value of A to the power of K, is kind of very, very hard or almost impossible, or you need the amount of universe equivalent computational power to reverse engineer K. It's impossible. Okay. So, okay, so let's do a briefer on what is a finite field, right? So since we already talked about this, right? So, okay, what is a finite field? So a finite field, which is a set. Let me try to pull out the exact definition here. So first, a finite field is a field. So this field actually has 2 binary operations. We call it plus and multiply, right? And then I would not actually go through all the like algebraic properties here, but we have this. So here is the list, right? First is that associativity among both addition and multiplications. I just show you what is associativity is, and the commutativity among both additions and multiplications. And also we have the identity element of both addition and multiplication. And then we have additive inverse, and we have multiply inverse. And then last but not the least, we have this distributivity. Distributivity, which means that we have such a fact. You can see there, in addition of defining these 2 algebraic operations, we have this distributivity, which sort of reviews the which sort of kind of like reviews the relationship of these two kind of mathematical operations. So I would not dive into super detail here. The fundamental reason here for not only for this specific finite field is that in most kind of finite field we're using, or in this particular finite field that we're taking this prime number, the discrete log is not hard. Unfortunately, you have to using something like RSA group. So RSA group is cryptographic primitives kind of popular before ellipse curve. And the problem of the RSA group is that nowadays you need to using 4096 bit for security. That's just very, very slow and very, very big. The proof will be gigantic if you're using an RSA group for the zero-knowledge proofs, right? So then let's get back to ellipse curve, right? Ellipse curve is defined over this finite field. However, we know the discrete log of the ellipse curve is hard. Okay, let's say how we can define this. How we can define this? What is this group, right? When we are talking about the discrete log is hard, the sort of first question we're asked is like, as we define the group here, right? What is exactly the group, and what is the group operation? Okay, so then let's go through it. So first, let's draw a picture of ellipse curve. I think it's good to have a visual understanding of the ellipse curve. So let's say we find like a 2 point, P and Q, right? So we know like P has an X coordinate, P has a Y coordinate, and Q has an X coordinate, and Q has a Y coordinate, right? So then we can define addition over the ellipse curve point. Right, we can define P plus Q equals minus R. So in fact, we actually define this P plus Q plus R equals to 0 by just taking a straight line over P and Q, and then you get R, right? And the cool part here is that both P and Q and R are all the point on the ellipse curve, and also they are all the integer point, and also they are all the over finite field, right? So then we have basically we have the ellipse curve. This operation is EC addition, right? Now, in zero-knowledge proofs or in ellipse curve mathematics, in cryptography, how we are defining this group is that we chose a point of G. And there are certain mathematical criteria how we chose a G. And for example, the Ethereum used like a ellipse curve BN354. And this G is chosen by a bunch of cryptographers. I think I forget exact group of people, but I think there is like a Barry Whitehead, there's a Sam Bowie, these kind of pioneers. They chose a point so that this point has a special special properties. I can dive into this what exactly special properties, but for time's sake, let's just take it granted. And now we have this point, and we know what is addition, right? So basically G plus G plus G. So this is easy add, right? Again, this is a group, right? If you are using the multiplicative notation, this becomes exponentiation. Then that's where it was not random. It's kind of random choosing, but it's not. So you basically run a bunch of simulation to get some properties. So one of the properties is that you need to have a, like this G, if you are familiar with group theory, it's one of the bases of the cyclic groups. And then the prime order of the group need to have a certain criteria. So it's random chosen, but there are some criteria. It's kind of like using some like a simulation chosen, such that it actually fulfills some like properties. Okay. So you can see here, right? Again, back to the group, right? So G here forms the base. Then let's try to actually define the group, right? The group that where exactly the discrete log is hard is that we need to define a group. Let's still use a G here, right? Of course, there is a zero and there is like a identity element, right? There's G. Then we need to define a number here. This number is R minus 1, right? And this group has a group order of R, right? And this R is a prime number. So, okay. So we also call this this R as a like a scalar field. Okay, now now let's get back to the topic. Like I said so much, right? Why I'm doing this. So in the I think most people are working on like Ethereum today. And if you want to do like a zero-knowledge proof cryptography on Ethereum, you are using this specific input curve called BN254, right? And this BN254 is defined on a finite field. And this is finite field, we call it FP. And this FP relatively have about 2 to the power of 254 bit, or 254 bit, right? And this finite field actually forms the elliptic curve. And for all the zero-knowledge proofs, because again, because the discrete log on the finite field is not hard, we need to choose a group element. And for this specific group element we chose, right, it forms a group. And for this group, it has a size or prime order. Then this group, we call it FR. FR is also about 254, but this FR is slightly smaller than FP. And at least you need to know these are two different numbers. So then we call this, we normally call this as a base field. We call this as a scalar field. Okay, so far so good. Okay, so now comes question. How many of you have using Circom to write a zero-knowledge proof circuit? Please raise your hand or like post in the chat. Okay. Anyone else? Okay. So let me ask you a question for the volunteers. Great, thanks for volunteering. In Circom, someone writing a zero-knowledge proof circuit, right? Okay, LeapSnark, that's great too. In Circom or LeapSnark, someone need to write a circuit. Let's try to write a single circuit, right? In Circom, so there is a thing called signal. Signal is kind of like a data type, right? You can define some variables. So let's say if you define a signal A, and if you define a signal B, if you define a signal, let's say C, and you write something like A plus B to C. So this is your Circom program, right? Let me ask you a question. This signal is a data type, right? And this signal is like a finite field or scalar or whatever, a number. What's the size of the signal? So before we're talking about non-native arithmetics, we need to talk about what is native arithmetic, right? What is the data type? You're using basically a zero-knowledge proof is arithmetic operations, and this okay. Why? Someone answered 256 bit. Why is that 256 bit? Okay, here I'm talking about precisely if you are using Gross-16 or Planck to writing a circuit targeted on BN 254. Okay, larger than R based on which field size? We have two field size here. Okay, good. We have some disagreements, right? I think this is really important if you actually ever write a circuit. If you write a program, like it's writing a circuit kind of just writing a normal computer program. The first thing first is you need to understand what is data type, right? It's a uint, it's 32-bit integer, 64-bit integer. Okay, so basically Shenzhen said it's a scalar field. Like iPhone said it's a base field. I mean, that sounds both reasonable. Can you guys articulate why it's scalar field and why it's base field? Remember, I told you fundamentally why zero-knowledge proof work, why crypto works. This need to reduce to some hard problems. And the hard problem we're reducing here is this discrete log is hard, right? And this is a homomorphic, this is a homomorphic operation. At end of day, it need to get to something like this. It's not just to how many bits. It has an exactly prime number. Like it's not just a bit. A bit is 2 to the power of something, but here it's a prime number. Yeah. Let me rewrite this. Let me rewrite this equation, right? That's what actually happens if you compile the circuits, right? As some of you already figured out, and as Xinjiang already answered, it has to be scalar field because at the end of the day, this need to turn to the discrete log is hard. Discrete log is only hard on the elliptic curve group element. And this particular group element we chosen having this order. So this is data type. So it has to be this prime number. You can check what is this prime number. There's tons of materials you can check. And first, it's roughly about 200 like a 4-bit. Second, and this is the base field. So sorry, this is first. This is okay. So get back to that, right? So then, what does it mean? So this means any finite field operations. So here we're saying finite field operations, not group operations, is because of pairing. Let me tell you pairing later, right? But that's so you can roughly see how we are actually building this how we are kind of actually encoding this kind of like arithmetic operations in CIRCOM, right? So here, this data type of the signal sort of have to be the size of the scalar field, or have to be the prime order of this the prime order of the cyclic group that were chosen, right? So this is called native operation, right? However, so before, so now let's pause here a little bit to see any questions, and let me myself get a water break. But first, feel free to fill in the questions in the group, and I will take a 2 minutes water break, and then come back. I will check the chat. Great. Okay, I'm back. So any questions? Basically, the computation of the behind the ZK calculation on the curve is correct. So that's the reason why, yes, exactly. That's partially the reason you have a big enough finite field, and also doing the group operation, and the group operation take a lot of time. That's why it's secure, and also why it's consume a lot of time. So, and when we try to aggregate a circuit, if one of the previous sub-circuit has some issues like missing some constraint, we can still get the aggregation result right. What do, like the aggregation circuit is just like a faithfully implemented verifier. If the verifier result is false, right, so the aggregation, you just get a false result, right? So this doesn't really matter here. It just like your proof, just the verifier circuit just tell you your proof is false, right? So okay, so now we get intuition, right? How does so the intuition here, we kind of intuitively and know, like in the zero knowledge proof, right? This arithmetic statement, how can we do the A plus B, right? But to build a arithmetic circuit, we need something like signal A, signal B. We need to something like A times B, right? Let's say equals to, we have a signal D equals to D, right? How do we do this, right? We understand, like finally in a group, right? We only have one operations, and here we're just like abusing the notation a little bit, right? So we're using this like a group element to do the multiplication, represent the multiplication. Represent addition in the circuit. Like how are we going to do? How are we going to do how are we going to do multiplication? How are we going to represent multiplication as an operation in the circuit, right? Like, so this is, and then that's intuitively why we need pairing, right? So Okay, so we get to how we are going to represent multiplication in a circuit. So here, then we actually need to introduce another operations on elliptic curves. And now we're actually not only like introducing operation on single elliptic curves. So we're actually introducing operations on multiple elliptic curves and multiple groups. So the general definitions of pairing is we have 3 elliptic curve groups. One is G1, one is G2, and one is GT. So pairing is operation. First, we call it E, and its type is G1, G2 to GT, right? So here X means Cartesian. Here X means the Cartesian product. So which means let's say for here, let me use still use A here, right? For A in G1, B in G2, and C in GT, right? We can define such an operation called A, B equal to C, right? And what is a property? What is a property of this pairing, right? You can think of kind of like a product. The most important algebraic property of product is that this is a bilinearity, or let's call it a distributivity, right? So more precisely, so this is actually means, let me just erase the C here because I want to use C for others, right? So this actually means I guess let me just using the multiplicative notation here, right? So you can think of this as a I will say this is like a left, this is like the right, this is like a right distribute, this is like a right distributivity. And we also have this like E, let me use a different word, AB plus EB equals to EA plus E plus B, right? I think someone write like a single variant. That's true, right? So this is basically, you can see this is actually defines this kind of like algebraic properties, defines the algebraic properties of the pairing. Sorry, the kind of algebraic properties of the multiplication, right? So then this pairing is being used. That's why intuitively why the more than zero-knowledge proof systems, at least a lot of them are using pairing, because intuitively you need to using pairing to sort of to represent the multiplications, right? So so here let me, okay, so now now we like intro pairing. So now let's get into the proof systems and proof aggregation, and why the and why the proof aggregation requires non-native arithmetics, and why we need that, right? So intuitively, so for all these proof systems people are using right now, right? So we can give a little bit sort of like a overview of the proof systems, right? So we just talk about like a Planck, Gross-16, and others. Let's actually get a review, sort of a high-level idea of the review of proof systems, right? So so we have some like a sort of a front-end programming language, right? Like a Circom, like a PO, like a NOR, right? These are the people use, right? And then this kind of represent, this program is just like a program to represent two things. One is a relation, and one is witness generation. So the under hood, there is a layer called arithmetization, which means we need to convert this program to like a polynomial equations to represent the relation. So we have various kind. We have R1CS, like we have air, we have Planckish, and now we have CCS. This is kind of like an R1CS like, right? So, and under the hood, we kind of need like a cryptographic compiler, and people also sometimes call it like ILP, right? So ILP is like a I think it's like a stand for interactive oracle, like interactive oracle. I forget the exact the abbreviation here. So but basically from the high level, this is a cryptographic compiler, and so this compiler, some people using SumCheck, and some people using like a PILP. And actually there are even people using like PCP. And that actually like have different kind of choices with this like cryptographic compilers. And then the final step is polynomial commitment scheme, right? So there is like a Hydrac, and then someone using the like a KZG, and there are people using like a Fry, and then there is like an IPA, and then there is KZG. And so basically this is a Spartan using PCP. This is Gross-16, and this is like a Planck or like a Halo 2 KZG, and this is like a Halo, the original version of Halo 2, right? And this is basically like I don't think there is a error here, and this is basically Stark, right? So that's sort of this like and by the way, this is this is kind of like a Marnie. Sorry, Marnie uses KZG. So from these pictures, right, you can see for the Okay, sorry, I think I missed some questions a few minutes ago. Okay, one simple question, G1 and G2 are the same EC but different orders. And the base point. I will answer your question. I will answer your question shortly, right? So I just want to zoom sort of I just want to sort of zoom out first, and to yeah, I just want to zoom out first to get a brief overview of this like proof systems, right? So and then I will tell you what exactly G1 and G2, because this question, so this is actually get back to the question on like which kind of pairing curve you are using, right? If your question is kind of Ethereum specific, then I have an answer. That's exactly what I'm going to tell next. I'll get back to this proof systems, right? You can see there are several things. At the end of the day, you need to using a polynomial commitment scheme. And this polynomial commitment scheme is either MSM based or it's pairing based, like KZG. So like Hydrock or like KZG, right? Or it's a hash based, like a Fry. Fry is a little bit different because for Fry proof, people normally don't use a Fry proof for the end proof, like set it on chain, because Fry proof is too big, right? You kind of have to convert a Fry proof to one of this like smaller proof, then you need to get to the MSM pairing again, right? And then fundamentally, like for the recursive verifier, we need to have a circuit that implement this MSM or pairing efficiently in the circuit, right? The question here is that on what field? What is this like MSM and pairing this operation of, right? Let's get back to the discussion is on this base field and scalar field, right? Would this MSM and the pairing in the base field or the scalar field? Why this MSM and pairing on the scalar field?
Because group operations are defined on the scalar field.
Remember, okay, so here the problem here is that, so think about that, right? We are actually implementing the circuit, and this circuit needs to implement the verifier algorithm. So we're actually doing the scalar multiplication. We're doing the scalar multiplication, but the operation is on the base field. So for example, how are we building? How are we actually adding 2 points? Yes, we're doing the scalar multiplication, but the arithmetics, the program we're running is on the base field. So for example, like you can check on some like a curve. At the end of the day, you need to operate. If you want to add these 2 points, P and Q, right? You kind of need to operate. You need to operate on XP, XQ, YP, and YQ, right? And these are when you are actually doing the operation, you're actually working on the base field. That's the circuit is, right? You see the disparity here. The disparity here is that in the recursive verifier circuit, right, you need to using the scalar field arithmetics to express base field operation. these two fields is very similar. They are roughly 2 to the power of 2 to 54 bit, but they're different, right? To do that correctly, it's not easy. So for example, a single native arithmetics, right? So let's say in the third column, you write a plus b equal to c. This is FR, right? Now that's fine. However, to do the field simulation, you need to break down that into different limbs. And there is a new, there are people usually using like a CRT, which is like a Chinese remainder theorem-based field simulation algorithm. This costs a lot of constraints. And roughly speaking, it costs like 20x. That's already an optimized implementation to 50x. Actually, this is not right. Actually, it's like 40x. This actually costs 40x to 50x more constraints if you are doing field simulation or simulating non-native field. Okay. So one of the project, the project I'm working on called Nebra, we are building the state-of-art non-native arithmetic circuits inside Halo 2. And we are at least 2x better than the state-of-art. The state-of-art is from the privacy and scaling exploration group. They're like a Halo 2 run and Axioms like a Halo 2 lib, right? We're 2x better than that, right? So that's sort of the critical piece we're working on. So get it back, right? So now I think it's time to answer previous person's question about on this pairing. What exactly is this G1 and G2 and also this GT? So again, let's write the pairing equation, E G1 times G2 to GT. On the BN254, we kind of know what is G1 is already, right? So we have this like a BNSFQ, and we chose a point, right? So this is basically the base curve. What is G2? G2 is a elliptic curve defined on the field extension. So a field extension, people usually write FQ2. It's just like think about like we have rational number. Now we have like a complex number, right? So or like this is like a two-dimensional vector space. So we can actually define an elliptic curve over the field extension, right? This is like a single finite field has 2 points. Instead of a single like a it's instead of like a single sort of like a integer, it's kind of like it becomes a vector, right? And so this is where G1 is defined. This is where G2 is defined, and GT is defined 12-degree extension, right? So roughly speaking, we have like a 254-bit. Now we have 2 times 254-bit. And this we have 12 times 254-bit. Right? That's also why the GT operation is very, very expensive. And if you want to do non-native arithmetic on G1, it's fine. G2 is worse. And the GT, that's the worst of the worst. That's also why, and because pairing, like we need to implement the pairing in circuit. That's exactly why like pairing in circuit implementation is so hard. Yeah, I think probably it's good to end here, right? So I probably don't have the time to dive into the Chinese remainder theorem-based approach, but So most people are using sort of the Chinese remainder theorem approach designed by a project called Aztec. Yeah. So that's their field simulation algorithm. Most people are using that algorithm in circuit to implement that. Okay. I will be sending the handwritings of this to the group. So is there a deterministic way to know the number of elements over a elliptic curve over a finite field? Yeah, of course. Yeah.
Okay, great. If you have any other questions, feel free to drop in the chat box. And maybe let's wait for another like 3 to 5 minutes for the final questions.
Great. Yeah, I can talk about a little bit about that, right? So I think not sure you guys are familiar with like Lagrange theorem. It's basically roughly talking about like how many elements like a group has, right? So mostly people can using Lagrange theorem plus a little bit other things to figure out. Yeah.
All right, great. It seems like we don't have any other additional questions. I believe all of us are in a group chat as well. Feel free if you have additional questions, and you can drop in a group chat. And thank you very much. Thank you, Professor Shumo, for all the sessions. Very informative and interesting mathematical logic behind all this like circuits. Thank you so much for your time. And let's call it a day.
Thanks for having me. Yeah, great. Thank you. Bye.
Thank you. Bye, guys.